Before understand what a graph is, let's discuss some linear data structures, like an array, where the information is indexed in such a way that we can access any element with identifier and index. By example, a book name and page are called linear data structures, because usually you have to check page by page until get the target. Computers do indexing from zero, but the length is counted in natural way. Using this format, data can be indexed into multiple dimensions. What you are seeing here is a two-dimensional array. So, if we want to access to the data on the second element of the third element, we write the identifier starting from 0 with the 2 in the first dimension and the 1 in the second dimension. Unlike humans, there is no limit to the number of dimensions that a computer can process. Let's name some other linear data structures used. The stack, referred as LIFO, where the elements are placed and taken only from the top. A queue, referred as FIFO, where the elements behave pretty like a shopping line. And a priority queue, where the VIP elements are processed first. Humans always try to process elements in linear ways. This doesn't work for computers. Imagine every processed search with linear methods. In that way, a single match could take days to resolve from the server. Another linear structure used are linked lists that behaves similar to a waiting room, where elements are not physically ordered and each one points to some next memory location. Crypto blockchains operate under this method to maintain a decentralized transactions traceability. There are good options to manage information in a nonlinear way, like hash tables. In this chapter we focus on graphs, which are composed of single points called vertices, and its connections called edges. Origin on mathematical concepts and directly related to the miracle of the AI. Self-driven cars, robots, along with human minds can be modeled as graphs in some way. By example, when you smell gasoline, your brain visualizes combustion engines using a neural network of memories, sensations, and connections. During this video, we will discuss non-directed graphs, so any of these connections can be written in any direction. If the graph involves any multiple connection between two vertices, it is called a multigraph, otherwise it's a simple graph. The degree of a vertex is determined by the number of connections that involves it. By example, in this graph, each vertex degree is denoted in this way. A subset of vertices and edges inside a graph is also considered a graph, better known as subgraph of G, and any standalone vertex is also considered a graph itself, better known as the trivial graph. A path is any route among connected vertices, involves start and end points. The path length is determined by the number of times that any edge is crossed. As the start the same as end points, the path is closed. The path is simple if all vertices are different and a trail involves different edges. Both cases without repetition. If the path is having the same start and end points involving more than two vertices, is called a cycle of length k. In this way we classify the path 1 as a simple trail path and the path 2 as a cycle of length 3. If all points are connected in a single network, it is called a connected graph. Otherwise, it is a disconnected graph, where its components can be classified as a connected component and isolated vertex of G respectively. A distance between 2 points is their shortest length, denoted in this way. Finally, A graph diameter is the longest distance between any pair of points. If a connected graph becomes disconnected by removing a single vertex along with its edges, it is a cutpoint. By example, we remove C and got two networks. By the other hand, removing A and its edges, this graph still being a connected network. So C is a cutpoint of G and A isn't. The same way, if removing a single edge the graph becomes disconnected, then that edge is a G bridge, otherwise isn't. The birth of graph theory dates back to 1736, when Konnigsberg inhabitants wrote a letter to Leonhard Euler about its city geometry. From this famous problem he stated the following rules applicable to any graph. Let's first explain what is a traversal graph. This can be crossed using all edges without crossing any one twice. If there are two or less odd degree vertex, the graph is traversable. This city contains 4 odd degree vertex, so it is impossible to traverse in this way. Similarly, if a graph can be traversed across a cycle, it is called Eulerian. A graph is Eulerian if all vertex have even degree. Continuing Euler's works, W.R. Hamilton classified graphs according to the existence of a cycle with unique vertex and hence edges. Unfortunately, there is no simple way to determine if a graph is Hamiltonian. This rule works in most cases, where n is the total vertex number, u and v any non-adjacent vertex pair, by example b and c. If the sum of degrees and the distance between both is greater than the total vertex number, there are big chances to traverse this graph with a Hamiltonian cycle. All graphs we saw until now are not weighted graphs, so any adjacent vertex pair distance is expected to be 1 in a non-weighted system. By the other hand, a map can contain information about the distance between 2 points, like in this weighted graph example. Also, it is common to use some terminology in reference to the graph structure. If it is possible to go directly from any vertex to any other vertex, it is a complete graph. If all vertices have the same degree, it is a K-regular graph, and a bipartition graph can be subdivided into 2 graphs so that each edge is shared by both. Denoted by T, a tree is a connected graph with no cycles. If there is more than one way from any vertex to any other vertex, then a cycle exists. A tree subgraph inside any other graph is called a spanning tree of G. By example, from this graph, 4 different spanning trees can be extracted. If it is a weighted graph, then a common problem in computer science is to extract its MST. It stands for minimum spanning tree. That is just the spanning tree with the minimum total weight. To do this, just remove edges in descending order without disconnecting the graph. A planar graph can be represented without crossing edges, otherwise it's a non-planar graph. By example, in this one right here, the BC vertex can be rearranged like this. Graph image or rearrangement is called a map. A map contains places called regions. By convention, the surrounding area belongs to a region contained into a square. A region degree is the number of edges contained in a region cycle. If both sides of an edge are involved, then that edge will sum twice. By example, the first region degree is 3, the second region degree is 5, and the fourth region degree is 3. There are important relations related to vertex, edges, and regions inside the map. The number of edges by 2 corresponds to the region's degree summatory. By example, here we have 7 edges, by 2 is 14, which is the degree summatory. And the Euler's relation states that the vertex number minus number of edges plus number of regions equals to always. By example, here we have 5 vertex, minus 7 edges plus 4 regions results in 2. What is a graph coloring? Is the assignment of a color to the vertex such that an adjacent vertex always have different colors. The chromatic number of a graph denotes the colors required. Now suppose a graph is enhanced. Well, generally speaking, 4 colors are enough to coloring any planar graph. Another common challenge is to assign region colors to a map in such a way that adjacent regions have different colors. So obtain this from that. Here is where the idea of a dual map or G single quote becomes useful, where its vertex denotes map regions and vice versa. In that way, work on the idea of vertex is faster than have to deal with geometrical places. Now, computers don't understand graphics. These are just visual mechanisms that scientists use to represent ideas. A graph is structured in adjacency terms. By example, in the adjacency matrix, all connections are visible in a two-dimension table. If it is a multigraph, then the number of edges is denoted and the adjacency list will be more efficient for programming purposes, where each vertex along with its connections is an arrangement element. Now, the way that data is located in a linear structure is obvious. Check one by one. But how data is located in a graph? Let's briefly introduce the most used techniques. The depth first search or DFS algorithm. Traverse a graph from the parent vertex down to its children in a single path until it reaches a dead end. When there are no more vertex to visit in a path, then backtrack to a point where it can choose another path. If there are no more options, then that point will be exhausted. The DFS algorithm is recommended where there are no cycles. That's why it's known as a tree search. By example, if the data we are looking for is in here, then it only will be located at the end of the process, slowing down the performance. Similarly, in the breadth first search algorithm, instead of exploring the vertex up to down level, all same level vertex are explored simultaneously, saving all the routes in a queue. When a vertex runs out of options, it is removed from the queue, and the process continues down in the next level. Now, another common problem in computer science is to find the most efficient path saving energies. In a simple graph like this, at first glance you find 2 ways to solve the problem visually. Depending on the vertex number, a complete graph like this is said to have 3 different Hamiltonian cycles. Now, in a complex graph like this, there are 12 different options to be found here. Not visual, easy at all. We apply the nearest neighbor algorithm. Take the less way vertex each time until traverse all. Question 1. Having this information adjacency matrix and degrees, find its graphic. This information is announcing how many connections every vertex have. So first let's draw what we have until now. If A is connected to every vertex, then there is a connection with C. B cannot have more than two edges, and D only have one connection. The remaining connection is between C and E. So finally the C degree is 2. Question 2. Let's suppose you enter the construction business and must choose a design to build a road in a single trail that starts and ends the same point. Remember, a path cannot repeat vertex, hence edges. A trail cannot repeat edges but vertex. A trail that starts and ends the same point is called an Eulerian cycle. So let's call back the Eulerian rules. This one right here doesn't match any Eulerian rule. This one can be traversed over an Eulerian trail. And finally, this one contains an Eulerian cycle. Now let's suppose you are the security manager, only have personnel to deploy 3 checkpoints. If we don't rearrange the network, then drugs will freely cross on these 2 edges, without disconnecting the cities. In how many ways it can be solved? This is reduced to find all the spanning trees, and yes, there is an expression to get the number of spanning trees in a complete graph. Unfortunately, it doesn't apply to this problem because there is not connection between A and C. So we have to manually draw every possible solution here. Question 4. Suppose you have to energize all the cities in this network. If the distances are known, find a configuration reducing the wire used as much as possible. This problem is reduced to find the G minimum spanning tree, or MST among friends. As we saw in previous examples, just remove the edges in way descending order without disconnecting the system. Question 5. We must evaluate and classify the following graphs in order to build a map over them. Remember, a map only can exist over a planar graph. In the first one, notice how B is connected to both side vertex, the same way as E. So it will be convenient to swap these two. In the second, we can get rid of these crossings by outside connections. Finally, there is no way to express this without crossings. So we will use the first and second planar graphs. Question 6. Give a complete description on G and H planar graphs. How many vertex, edges and regions they have. Also get the degree on the outer region and check them with the Euler's formula that says the region's degree summatory equals to the double of edges number. On the first graph we have 6 vertex, 9 edges and 5 regions. To check the Euler's formula, let's compile all the regions' degrees. 3, 4, 4, 3 and 4 equals to the double of 9. Yes, now let's evaluate the H graph. Question 7. Having only their adjacency matrix on the unweighted graphs G and H, find their graphic representation. The adjacency matrix contains implicit information about the vertex, so begin with naming each one, then place the vertex and do the connections. Question 8. From its visual graphic, find the weighted matrix and any linked representation of Y. Now, for the linked representation, the most common method is to list a connection array for each vertex, in such a way that along with the weighted matrix, we give a complete description to work with. This has been all for today's video. By the way, if you want to learn from more advanced exercises, a link in the video description will be available. Thank you very much for watching our video and see you next time.